I'm Tom Edwards. I'm an AWS Certified Solutions Architect and MCSE. For the duration of this video, I'm going to provide a hands-on deep dive where I'll do the mouse clicks and the keystrokes behind creating an elaborate AWS Virtual Private Cloud. By way of introduction, I've been in IT for over 20 years. I was a 12-year Microsoft veteran, and I'm also an inventor. I have 2 U.S. patents for systems and methods to enhance virtual disk performance that are cited by Amazon, IBM, Microsoft, Citrix, Red Hat, and other technology companies in their own patents. I was hands-on during the early years of virtualization. So I saw the writing on the wall and realized that Fortune accounts, or any data center for that matter, would want to take advantage of the same economies of scale. And so I left Microsoft and started a software company, and almost overnight we grew to 100 employees, and we wrote software that migrated workloads to virtual clouds. We had over half of the Fortune 50 as accounts, and we had many of the Global 2000s as accounts as well. So I am pleased to be here to talk to you about creating a virtual private cloud, because that's really the heart of the cloud, is the VPC. So the deep dive is, here's what we're going to create. We're going to create a VPC, or a virtual private cloud, in one region. We'll have multiple availability zones, multiple subnets. We'll have public routes, private routes, an internet gateway. We'll have NAT gateways, public IPs, private IP pools. We're going to create a multiple AZ application load balancer. Then we'll create 2 Bastion hosts to deploy in our public subnets. Then we'll create a web app and a database and deploy them in our private subnets. Then we'll bake in security through security groups and NACLs, and we'll show all of that. So the scenario is that we're new to AWS and we don't know where to start, but we do have objectives and we do have requirements, and both of those are shared by the business and the technology groups. And that is that we have an application that needs to be available, secure, and scalable. So the objectives are clear. It's time to begin. AWS has a global infrastructure, a global network, and inside of that global network, nomenclaturally, we have regions and availability zone. A region is a geographical area. That's Virginia, Tokyo, Paris, London, Ohio, Ireland, etc. There are 24 AWS regions across the globe, and then in each region, there are a minimum of 3 availability zones. An availability zone is a discrete data center within a region. And when you deploy resources across availability zones, you gain reliability and fault tolerance. And in some regions, North Virginia is an example, there are more than 3 availability zones. North Virginia, as a matter of fact, has 6 currently. As we speak, there are 77 availability zones across all AWS regions. So what is it that we are creating? From a simplified standpoint, we have the AWS cloud, and in that we have our virtual private cloud. And in the virtual private cloud, we have an availability zone. The availability zone is where we place our resources. And in this example, our resources are a workload and a security group. A workload in this demo, or this hands-on, will be a web app and a database. A workload is also a Bastion host in this example, but a workload to you could mean your ERP system. It could mean your CRM system. It could mean your Exchange server. It could mean your PostgreSQL server. It could mean any number of things, Apache, etc. So a workload is simply what you deploy, and you deploy a workload in an instance. An instance is referred to as what runs your compute and your storage. So a very small instance that you could scale horizontally would be something that would have like half a gig of RAM. An instance that size might cost you $10 to $20 per month. Whereas they also have at Amazon much larger instances for compute intense applications. For example, the P4 instance type is 8 GPUs, 400 gigabits per second network, 96 vCPUs, over a terabyte of RAM, and EBS bandwidth of up to 19 gigabits per second. So the scalability is quite massive. So what is it that we're creating? Well, this is exactly what we're creating. We're looking at the AWS cloud, and in the cloud, we're going to create a VPC, or virtual private cloud, and that is something that is at the region level. And then in the region, we're going to deploy our VPC across multiple availability zones, Zone A and Zone B, and then each availability zone will have a public subnet or a DMZ. A DMZ is the demilitarized zone, and that is where you place all of your publicly addressable resources, such as your Bastion hosts, your ALB, your NAT. And then behind the DMZ, we'll have our private subnet, and that's where we will deploy our resources, such as our web app and our database. And then in each, we're going to create one route table per subnet. And we'll have 4 subnets, so we'll have 4 route tables. We'll create an internet gateway, 2 NAT gateways, 2 security groups, the ALB, the 2 Bastion hosts, and the web server. And that's what we're doing. And this is what it looks like with the ELB here, the Bastion hosts there, and the instance types there. So let's go ahead and get into the hands-on portion of the demo. Okay, so we're in the management console here, and we're going to go to VPC, and we're going to create a VPC. And it's important to note that the VPC is the heart of the cloud. It's where you deploy your workload. It's where your applications sit. It's where you control inbound and outbound traffic. It's where you go to configure the particulars of all of the security layers from a protocol and port perspective. You notice here under security, you have network access control lists or NACLs, and then security groups. It's where everything is configured that makes the VPC secure and the whole bit. So what we notice is that we already have a default VPC, and the default VPC comes with one route table. It comes with one network access control list, and it's basically just a default, simple, stripped down VPC that we could use when we're new to Amazon Web Services. But when you become serious about deploying resources, be they a development, test, or production, you will get equally serious about architecting a network that has availability, reliability, fault tolerance, and security built into it. And that's what this session is all about. So let's go ahead and create our first VPC, and we're going to call that our production network. And our CIDR range is going to be large. So we're going to go to /16 CIDR range. If you're not familiar with this, CIDR stands for classless inter-domain routing, and the /16 is basically a prefix, and it's very simple. You start with /0, meaning that the prefix is not full. You have all 32 bits available, and it goes all the way up to the /32, and that's simple. It means that all 32 bits are defined or full. So you have from 0 to 32 bit prefix, and so it will become clear what we're doing here. So the /16. Now, what does that mean from an IP standpoint? Well, it means that our range of IP addresses is we're taking a base of 2 and an exponent of 16. Again, 16 from 32 is 16, and that gives us a total of 65,536 IP addresses. In a range for a production network, that is more than enough, so that's fine. So we've created our production network. This gives me a pause to point out one thing very specific, and that is tagging. You notice that under VPC, we have a name for each of our two items here, production network and default VPC. When we create a production network VPC, it created for us a route table. See right here, production network routing table, and it's not named. So let's name this route table. We're going to say route table not in use. Since we're creating specific route tables, we're going to make this main route table, see main, yes, we're going to make that main route table not in use. And getting back to the tagging, go to network access control list for production network. You notice that there's no name for the NACL that was created. So we're going to say this is the NACL for our production network. Now, the bugaboo here is that you should get into the habit of naming things early on. The reason is that over the weeks or months and longer that you use AWS, if you do not name items, whether it be in the UI or log files, you'll scratch your head wondering what in the world things are that are not named. So it's not a good idea to leave things unnamed. So where you can, please name things. So now that we have defined our NACL and our main route table, and we've created our VPC, it's now time to create our subnet. Now, subnets are tied to availability zones, and in each subnet we want to utilize, we'll create a public and a private subnet. Now, typically, a public subnet is where you'll deploy only a few resources, like an application load balancer or a Bastion host. And your private subnet is where you'll have internal corporate resources. So the range for IP addresses in an internal private subnet is much higher than the range of addresses that you'll have in a public subnet. So it's important with these considerations in mind when you're considering the size of your CIDR range. So for our production subnet, first is going to be our DMZ or our public subnet. We're going to call it DMZ subnet A. And then we're going to put subnet A into the production network. Our availability zone is going to match up to A. And then our CIDR range, since it's a public subnet, is going to be small. So we're going to choose a small prefix, and the small prefix 27 from 32 is 5. So when we go over here and say base of 2 and an exponent of 5 gives us 32. So we have 32 IP addresses in this public subnet. We're going to create our second public subnet, which is going to be B. And our VPC is production network. Our availability zone is B. And our CIDR range here is going to be equally small, 168.1.0/27. So a prefix of 5, 27 from 32 gives us number 5. And then that gives us our 32 IP addresses. So our two public subnets are created. Now let's create our first private subnet. It's going to be named PVT subnet A. And it's going to go into our production network. It's going to match up with our A availability zone. And our CIDR range here is going to be much larger, 68.16.0/20. So our prefix will be 20 from 32. Our prefix will be 12. And that tells us a base of 2, exponent of 12. We have 4,096 IP addresses in this range, which is perfectly fine for a internal corporate network. And then that is our first. And then let's finish with our last private subnet with a production network to the B subnet. The CIDR range here is going to be similarly sized, .32/.0/20, so 4,096 addresses. So we've created our subnets very quickly here, and what we need to understand here is what we have is a theoretical segmented network. And what is next? Well, we have to design our traffic. Implicitly, our VPC has a router, as an actual router, and we need to set up route tables to control traffic. Now, this is potentially a confusing topic because we choose how many route tables are needed. We have two types of traffic. We have the type DMZ and the type PVT. So with two traffic types, does this mean we should have 2 routing tables? But we have 4 subnets. So does this mean we should have 4 routing tables? Well, the answer to that question is ultimately routing is about the subnet and not about the traffic. And the objective of our subnet and the objective of the VPC and our deployment in general is availability in the case of an outage. So if we do not explicitly associate a subnet with a particular route table, the subnet is implicitly associated with the main route table. And as we already showed, we do not want to use our main route table. And the reason is because we have more than one subnet. As a matter of fact, we have 4. So since we don't want to use the main route table here, we are basically faced with confusion by the choice. On one hand, a subnet can only be associated with one route table at one time, but you can associate multiple subnets with the same subnet route table. So what we need to do is simplify this. So what simplifies matters in my mind is knowing that there are limits. At AWS, they give you a limit of route tables per VPC. The limit happens to be 200. So 200 route tables for one VPC is a massive number, and that provides us with massive granularity. So we're only dealing with 2 or 4 route tables here. So having a limit of 200, whether we go with 2 routing tables or 4, either way, we're fine. But it comes down to a rule of thumb, and that is that a subnet can only be associated with one route table at a time. And we're designing for granularity for a singular purpose, availability, in the case of an outage. So shouldn't that mean 4 route tables? Well, let's go back to the use case. If you have a DMZ traffic across 2 AZs, that implies 2 disparate subnets. And if an AZ has an outage and you have a single route table for your 2 subnets and 2 AZs, this isn't granular enough and doesn't meet our objective of availability. So if we get 200 route tables per VPC, then why wouldn't we use all 4? Simple, right? It is to me. So the bottom line here is that we need our traffic to never be impacted for any reason. So let's go ahead and create 4 route tables, not 2. So let's go to our route tables, and we're going to design 4 route tables. So we want to create 4 route tables, right? So we create the first one. It's going to be called DMZ route table A, and it is part of the production network. The second route table will be called route table B, again associated with the production network. Now we're going to create our private route tables, A with the production network, and B with the production network. Okay, so now that we have created our route tables, we need to go and associate each route table with the appropriate subnet. And the rule of thumb here is that a subnet can only be associated with one route table at a time. So we're going to meet that rule. So let's start with our DMZ subnet A, the route table for the DMZ subnet A, DMZ route table A. And then our DMZ subnet B, the route table will be DMZ route table B. Then we'll start with private subnet A. The route table will be private route table A. And then private subnet B will be associated with private route table B. Okay, so we've met that rule. Okay, so by default, VPCs do not have internet access, so we have to do what? We have to create an internet gateway. And there's only one internet gateway that can be attached to a single VPC at a time. And as I said, VPCs don't have internet access by default, so we have to create an internet gateway to have internet access. You notice that this internet gateway, the default, is already attached to the default VPC. And since we have our own VPC called the production network VPC, we have to create a gateway for that. So we're going to call this our production gateway. And once we create that, we then attach that to our production network VPC. Okay, so now that our production gateway is created and assigned or attached to our VPC, we still don't have internet access. And the way in which we create or grant internet access to our DMZ or public subnets is by associating a route to the new gateway. So we're going to do that by creating a route 0.0.0.0/ the prefix of 0, which means the internet, and we're going to associate with an internet gateway, and that's the new production gateway that we just created. And we're going to do the same thing with our DMZ route B. So add the route of 0. The entire internet to our internet gateway, which is the production gateway. Click Save Routes, and now we have internet access to all, or I should say both, of our public subnets. Now we've routed our public subnets to the internet through the internet gateway, but our private routes are set to route internally addressable IPs only, or local, and so there's nothing else to do, right? Well, you notice that our private route B is routing locally, internally, and our private route A is routing internally, locally as well. Now, if the private routes require internet access, how do we do that? Well, we need a NAT gateway, and NAT, or Network Address Translation, allows internal IP to go outbound. And we are deploying multiple AZs, so we match the number of NAT gateways that we need to the number of AZs. So we have to create 2 NAT gateways, and the max number of NAT gateways that we can have per AZ is 5. So needing only 1 per AZ is perfect here. So let's go ahead and do that. So to do that, we go to our NAT gateway, and we create a NAT gateway, and we select our public subnet. That's where we're going to place our NAT gateway for the A network, and we're going to create or allocate an elastic IP. And you'll notice here that there is a publicly attached IP address with this NAT gateway, and then we create the NAT gateway, click Close, and then we create our second NAT gateway, and we're going to place that into the DMZ subnet B, and we're going to allocate another elastic IP address, which gives us the public IP that you see here. And then once that's done, you click Create, and it will go off and create these NATs. Let's go ahead and pause the video and wait till they are both available. Okay, so now that our NAT gateways are available, we notice that we have not tagged or named them, so we need to do that. Let's look at the subnet that we assigned, subnet A. So this will have a name, it'll be NAT A, and that would mean that the next one is automatically going to be B, since we only have 2 here, NAT B. Now, once these 2 NATs are named and created, it's important to go and edit the route tables for our private route table A and private route table B. So route table A, currently, the route is destined local or internal only. We're going to create a route, and that will be the internet, and the route will be associated to a NAT gateway. The NAT gateway, since this is the A route table, will be assigned to NAT A, and then we go to our route table B for private and edit the route and add a internet only to the NAT gateway B and save the routes, and we're all set. Okay, so now that the construct of our network is complete, the thing we're missing is security. So we have to create security groups that contain the rules that allow the PVT application to communicate to the DMZ via the ports or port that we need. And if we go to security groups, you'll notice that there are no security groups that define these criteria. So what we need to do is, since we're, in this example, we're deploying Windows Server, is that we need to allow an inbound rule for TCP on port 3389. If this is a Linux machine, we would do the same for port 22 for SSH. But so we're going to create 3 security groups, one for RDP, one for HTTP between the DMZ and the private, and then we're going to create a security group rule for the entire internet over port 80 to get into the ELB, or the Elastic Load Balancer. So with that said, it's important to note that the security parameters or security groups should allow inbound rules to apply only to another security group or groups and not the entire internet as it pertains to traffic between our DMZ and our PVT. And so we'll create one security group for our rules for TCP port 3389 and one security group for our rules TCP port 80 between the DMZ and the PVT. And then we'll create our third security group for our load balancer from the internet. So let's go ahead and do that now. Let's create a security group. We're going to call this first security group RDP from DMZ to PVT. And then we're going to select our VPC, which is a production network, click create. Because that's the first security group. Now you notice that it did not name it with a tag, so let's name that. Then come over here and we're going to name this one. It's going to be HTTP from DMZ to private. Then we're going to select our production network. I'm going to go ahead and name this as well as the tag. Then we have one final security group we're going to create, and that's going to be HTTP to ELB from internet. And that will be our production network. And then lastly, let's go ahead and assign a tag name to that. Okay. All right, so prior to launching workload instances into our VPC, I want to create a load balancer. So we do that by going into our EC2 experience, which is where you find the load balancer configuration interface. Click load balancer and then choose to create a load balancer. For this particular application, since it's just HTTP and HTTPS, we will choose the application load balancer, which serves just those protocols over TCP. And we will select that and just name using plain language, production ELB. And it's internet facing, and our listener, just for purposes of the hands-on portion, will be HTTP. Now, if this is a production system, we would also select an HTTPS for SSL or TLS listening on port 443. But since I don't have a certificate, we're just going to use the HTTP listener. And then for the VPC, we're going to select our production network, and availability zones will be A and B. The A availability zone will pertain to our DMZ SNA, and the B availability zone will pertain to our DMZ SNB. And then we go and click our security settings. And if you recall, we created a security group for our HTTP to ELB from the internet. So we will make that selection for our security group, and then we configure routing. And the routing is pertained to instances, and an instance is our workload. So we're going to call this production target group. And we'll again choose the port 80, and our protocol will be HTTP, not HTTPS. Now, if we wanted to, in a production environment, we would go ahead and configure our health checks to make sure that before traffic is routed to a particular host or workload, that the workload is deemed healthy by the ALB or the ELB. But it's not necessary here to configure any advanced health checks. We'll go ahead and go with the defaults, and then we register our targets. Now, we have yet to deploy our workloads or our instances into the VPC, so there are no registered targets to add here. But once we have deployed our workload resources, we'll come back into the ELB and we will register those targets in this interface here. But once we have completed that, we go to review and make sure that everything that we have set up is indeed correct. And once we've done that, we click create, and in about 2 seconds, our ELB is ready to go. Now it's time to go and launch our workloads into the VPC. Okay, now that we have our load balancer set up, it's time to launch some workloads. So the first workload we're going to launch will be a Bastion host. We will launch 2 Bastion hosts, one in our A subnet DMZ, one in our B subnet DMZ. So let's go ahead and right-click Bastion hosts, choose to launch. We're going to select just the T2 micro instance type, and we're going to select our production network and our DMZ SNA. We will select to add storage, click to create a tag, and the tag is going to be a name tag, and it's going to be the value of Bastion A. Click configure security group. We want to select an existing security group. RDP, actually what we need to do is create a new security group, because we did RDP from DMZ to PVT, but we did not do RDP from the internet. So we're going to create a new security group. We're going to call this RDP from internet to DMZ. From internet to DMZ, RDP, TCP, 3389 is the port, and the custom is everywhere. That's a bad rule. So what we want to do, when I say bad rule, it means that everyone on the internet can access, if they know the IP address, this Bastion host So what we want to do is limit it to only my IP. So my IP, that means that only my specific IP address or my corporate network can access it. So review and launch. So that was a Bastion host to the DMZ SNA. We're going to do the same thing to the DMZ SNB, the production network, DMZ SNB. Click Add Storage, Add Tags, Name, Bastion B. Configure the security groups. We're going to select an existing security group, HTTP from Internet to DMZ. Click Launch, Launch instances, and inside of a couple of moments, we've launched those instances. Now we're going to do the same thing with we have a web application and a database, which is basically WordPress, that we're going to launch into our internal subnets. And we're going to right-click and select Launch, configure the instance, add it to the production network, and this is going to be launched into a private subnet A. Add tags, and we're going to name this Web Database SNA. Configure a security group. Select an existing security group. It's going to be HTTP from DMZ to PVT as well. We're going to do HTTP and RDP from DMZ to PVT. Review and launch. Click Launch. And then go and configure and launch our last instance into our private subnet B. The default network is going to be production, private subnet B. Our storage is fine. Our name will be Web Database Subnet B. Launch. After we select the security group, will be HTTP from DMZ to PVT and RDP from DMZ to PVT. Review and launch. And we'll come back to this once all of our hosts are launched and available. Okay, now that our workloads are launched and available and all running, you'll notice that the Bastion hosts, the top two, have public IP addresses, and the bottom, which are running in our private subnet, do not have public IP addresses. So the first thing we need to do is go back to our EC2 experience and to our load balancer and register our two private targets for the load balancer. And the way in which we do that is pretty straightforward. We go into our listeners and choose to edit our production target group. And then once we're here, go to targets and we register targets. The targets we're going to register will be our web and DB, SNA, and SNB. And once we do that, we include as pending, and then they're put into the pending state. And then what happens is after the health check is done on these two instances, they are put into healthy rotation. And you can come back here in the ALB and check the progress, but it only takes a moment or so before the instances are available and we're ready to go. Okay, now that our two targets seen here are registered in the production target group, and you'll notice that they're both healthy. If I were to go to my load balancer and go to the description, copy the DNS name to the clipboard, go to a new tab and paste that, you'll notice here that the private subnet A is showing content that exists on that web and database server, and that if I refresh the page, that web server B is showing, and all links work fine. WordPress A, WordPress B. So indeed, our Elastic Load Balancer is working, and we'll come back and create an outage scenario so we can see how the Elastic Load Balancer takes care of health checks and routing traffic. But what we want to do now is take a look very quickly at the security that's baked into our environment here, or our VPC. So we have Bastion A, B, WebDB A, and WebDB B, and we want to look at networking. So the top two, which are our Bastion hosts, are the only hosts that have a publicly addressable IP address. The two lower are our private resources. They do not have a public IP address. Now, if we're to take a look at security from a security group's perspective on our WebDB SNA, you'll notice that there are two security groups that we applied to this resource, and they are both internal only. So we applied an RDP from DMZ to HTTP and an HTTP from DMZ to BVT. So that means that all of the sources that can access this resource all must exist from an internal resource, 192.168.0.0/16, which are internal only addresses. So we have the security set up properly for the DB SNA, and we take a look at the DB SNB, the exact same security groups applied to this resource specifically. Same exact thing that we just saw. So what that means is that we are completely secure from a lockdown perspective. There are no potentials in play here for anyone to gain access directly through RDP or any other means to do anything destructive to these two internal resources. The only way in which you could gain access to these resources is through RDP. So when we look at RDP here, the security group specifically, let's look at security. We have RDP set to gain access to the DMZ from the internet. But remember, we specified our source. Our source is our corporate network. So the only person that could gain access to any internal resources would be a person from our corporate network. Obviously, you would have to have username and password to do so, but we do have that. So let's go ahead and log in to Bastion host A. We'll say connect, and we'll download an RDP client. What I want to do first off is I want to edit that client, and I want to limit the display so it doesn't take up the full screen. And once we're in, enter in the correct password, and we are into our first Bastion host. And this Bastion host is Bastion A. See Bastion A right there. The next thing we're going to do is we're going to connect to our Bastion B host. So let's go ahead and download the RDP client for it. Download, same thing, show in folder, right click, edit. And once that is up, let's see here, right click, edit. We want to limit the display. I believe I chose 800 by 600 for our RDP session here. And this is going to be to Bastion B. And there we go. So we have two hosts, Bastion B, Bastion A, and there we are. So I have the desktop set up to automatically connect to the back end. So we have Bastion B, and Bastion B connects to 192.168.35.214. So let's look at that. Bastion B connects to that address there, 35.214. Bastion B connects to subnet B, and that's 35.214. So if I click on networking, indeed it is 35.214. So let's go back to Bastion B and select connect via RDP, and it goes right in. So let's enter in the correct password. And from this Bastion host, we get direct access to our web and database server. We're going to do the same thing with Bastion A here, just to make sure that our connections are looped correctly. Go ahead and take that, edit the RDP client, and it says here that our address is 23.101. So we go to our Bastion A network, which coincides with WebDB SNA, and it should be the same network address, 23-101. So let's go back to Bastion A, 23-101. Indeed, it is correct. So I click connect, and it asks me for my password, and I enter in the correct password, verify that I want to connect, and indeed it connects right in. So let's go ahead and take a look at a couple of things here briefly. From a management perspective, if I were looking to manage the back-end resources, I would have to use, and that is the purpose of a Bastion host, I would have to use a Bastion host to connect to these backend resources. And I would use, for example, this is WordPress. I would use localhost/wp-admin, or if I were using my PHP admin, I could use that interface to manage MySQL directly. But in essence, this is where we go to manage those resources directly, the Bastion host. And then from the Bastion host, we would use RDP to connect into, or we could use UNC or Universal Naming Conventions to connect to resources and edit files directly. But in essence, that is what we have. Now let's go ahead and look at creating an outage scenario and see how the Elastic Load Balancer handles that. Okay, so we'll keep those up. Let's go to an instance, and we're going to take our WebDB SNA, and we're going to stop that instance. As that's happening, let's go back to our load balancer and go to our description, copy the DNS name, go to a new tab, paste and go, and see what happens. So our A site is being drained, and the load balancer obviously sees that it's being drained. So there is there is nothing going on here from a reload standpoint. So it's the ELB notices that the status is no longer healthy, and it is making sure that traffic is only destined for the B site. Now, if we go to the load balancer, if we were to go into our listener, into our production target group and do a refresh, you notice that the target is in a stop state, and the target is the web SNA. So let's go back to our web page, reload, 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 and indeed the ELB is working correctly. It notices that the target is in a stop state, so it takes it out of rotation as a registered target. Now let's put it in pause the video and go back and restart our instance and see what happens. Okay, we are here. Let's go ahead and create a start sequence. And you notice that it is pending. So if we go back to our load balancer and go to our target, to our listener here, you notice that it's going to continuously ping the target group and this server specifically for a change in status. You'll notice that the target registration is in progress, so the status is being initialized, and it won't take very long for this server to be up. And once it is, then it will be put into healthy rotation. All right, so after just a few moments here, our status is healthy, and we go back to our page here and do a refresh. There, site A is back up and running. And let's go back to our instances and let's shut down site B. Our instance state, choose to stop, go back to WordPress, see how long it takes for the failover to stop. There, it's almost immediate. As soon as there is a change of state in the ELB, which picks up a change of status, the target is no longer in rotation. So the status is changed. The target is in a stop state, and going back here, reloading, it's not going to serve up and give us an HTTP 500 or 404 error. So that is the demo. I hope you enjoyed it. And if you have any questions, feel free to leave comments.